Welcome back. Let's talk more about equilibrium. This time, we are going to use that equilibrium expression and we're going to manipulate it mathematically. So, what can you do with this? Now, it's going to look very familiar because we've done similar things when we were doing thermodynamics and kind of think Hess's law. So, technically, this isn't Hess's law because it's not thermodynamics, but it's kind of the same idea. So, I'll go over these words and then, of course, we'll go over to the whiteboard. All right, so the mathematical use of the equilibrium expression. There is something called the coefficient rule, which in a nutshell means if you multiply the coefficient by a number, whatever you do to the equation, you take it to the power in the equilibrium constant. So if you double it, you square the constant. If you triple it, you cube the constant. Okay, so that's the coefficient rule. The reciprocal rule is if you turn it around, you invert. Remember, in thermodynamics, you just took a negative. So if it had been a positive, you take a negative. In equilibrium, if you turn the equation around, you invert the equilibrium constant. And then here's what looks like Hess's law. And some of you are thinking, what in the world is Hess's law? Okay. You may add up as many equations as you want until you get the desired equation, but instead of adding in equilibrium, we would add them together, but instead of adding, you would multiply the K values together. All right, let's go over to the whiteboard. All right. The math of the equilibrium expression. All right, so which one should we do? You know what? Let's go back to H2 plus N2, making ammonia. All right, so I know K is equal to NH3 over H2 N2. All right, that is my equilibrium equation and my equilibrium expression. Now, what do I want to do to it? I'm going to multiply it through by 2. Okay. So my new number is 6 hydrogens, 2 nitrogens is going to make 4 ammonias. What is that going to do to my equilibrium expression? Whatever I did goes to the power, and I still use the coefficients of this new equation. So this one would be 6, not 6. This one would be 4. This one would be 6. And this one would be 2. All right, that probably makes perfect sense, but it's the understanding of the relationship between the two that is very important. So I'm going to call this one K1, and I'm going to call this one K2. So K1 is equal to, how is K2 related to it? So K2 is equal to that squared. Now, again, I know that's not making much sense right now. I just want you to see the relationship between them. The K values are just being manipulated because I'm doing something to the coefficients, but they mean something, okay? And they're related. So let's try another one. Let's turn it around. All right, so now it's 2 ammonias is equal to, not equal to, hey, it's a math class. Feels like it. All right, the new equilibrium expression, I'm going to call it K3, is now H2 cubed N2 over ammonia squared. Okay, now K3 is its own entity, but I want to know, how is K3 related to K1? So K3 is really the inverse of K1. So I can call it something new, but what is its value? If I have the value of K1, then I would play with it. So let's take a look. We're going to pretend that this math is easy, and we're going to call that 2. All right, so K1 is 2. So that belongs to that very first equation. Well, if that is true, okay, if that is true, 2 squared is equal to 4, and that would be the doubled equation. But the relationship, okay, if I want to call this new thing K2, how is K2 related? It's the original that's been squared. So K2 is equal to 4. Or I could just write it as that, okay? So if I invert it, this new K3 is 1 over 2. Or I could have written it as 1 over K1. All right, they're all related. They are all related. But don't forget, you can create a new variable. Instead of keeping the original K1, you could call it K2, but there is a relationship between those two things. All right, so that is the 2 rules that we started with. So the multiplication rule, okay, the coefficient rule, and then we have got the reciprocal rule. Well, what if I use multiples? And that is probably the more interesting question. Let's multiply them together, shall we? And I'm going to use really generics. I said multiply, I meant add. So we'll call that one K1. And we will say D goes to E plus 3F. And we will call that one K2. All right, let's just add them together. And this new equation would be A plus D. I said D and then wrote B. Okay, B is in there though. Oh, jolly, ugly, ugly, ugly. A plus 2B plus D is in equilibrium with C plus E plus 3F. Right, that is my new equation. And the new K is K times, or K1 times K2. So I can manipulate as many equations as I want to come up with a new K value. And I'm now going to show you a real life one. So H2, let's do SO3. So H2SO3 acid can lose 1 proton, and then this piece, the conjugate base, can lose another one. Yeah. Nope. Already lost you. This one would be called Ka1 because it's the first proton coming off. This one would be called Ka2 because it's the second one coming off. And if you add them together, This one and this one cancels out, and H2SO3 has 2 protons plus a sulfite. And if you want to know this new K value, how do we want to call it? We're going to call it the K of both. It's Ka1 times Ka2. And so we can manipulate those any way we want as long as we follow the rules. If I had turned it around, okay, let's get rid of this one. All right, so we're going to use this equation again, and we are going to do A plus 2B is going to go to C. So that K1, um, what should we do to it? You know what? We're going to multiply it by a half. What you do to the equation, it's to the power. And remember, anything raised to the half power means square root. All right, and I'm going to turn the bottom one around. So 3F plus E is in equilibrium with D, but I have to invert that one. I have to invert that one. And now when I add them together, I would get 1/2 A plus B plus 3F plus E is in equilibrium with a 1/2 C and a D. And my new K value, okay, so my new one would be the square root of K1 over K2. All right, in the handout, there's a few problems for you to play with. And now let's go back to our notes. All right, so that is what we just did, is the rule of multiple equilibrium. It looks like Hess's law in thermodynamics. And before we end this one, let's talk about what is K. Yes, Jolly, it's the equilibrium constant. Thank you. Yes, it is. But what does the actual value of K mean? If K is greater than 1, it means products are favored. If K is less than 1, reactants are favored. If K is equal to 1, you're in perfect equilibrium, and neither are favored. They're equal. So if you're looking at your sheets, the orange sheets, you can kind of see exactly what each of them are doing. Back to my whiteboard. All right, and again, just making up these numbers. So if I have a K is equal to 2.3 times 10 to the minus 6, and I have another one that's 1.2 times 10 to the 5th, I have another one that is 0.1. Oh, let's see. 1.8 times 10 to the minus 5th. Ooh, let's make another crazy one. 2.1 times 10 to the 20th. All right, so all of those values are equilibrium numbers, and we're going to compare the magnitude. Okay, so the -6 means that K is smaller than 1, and so reactants are favored. So if we wanted to, we could draw a big old arrow on the side heading to reactants. This one, K, is greater than 1. And in fact, those two, it's much smaller and much greater. So this one, products are favored. Ooh, this one's close. Okay, that one is close, but technically it is still less than 1. So reactants are favored, but it's awfully close to being equal. Okay, it's awfully close to being equal. Ooh, -5. Ooh. K is much smaller than 1. So reactants And then this K, wow, much larger than 1, so products. So the further away from 1 you get, the less it's in true equilibrium. So one side is favored highly over the other. And that is the magnitude of the equilibrium expression. And if you're looking at your reference sheet, if you'll notice, all of those K values favor reactants. So weak acids, by their very nature, are weak, which means they don't favor products. So we expect K values to be less than 1. And if you look at those numbers, the K values for the acids, the Kas, are less than 1, indicating that products are not favored, reactants are, which means it doesn't want to lose its proton. So those are technically weak acids. If you look over on the other page at your KSPs, all of those are smaller than 1. And in fact, there's some that are crazy small, which means they are insoluble solid. So KSPs less than 1 means that the solid doesn't want to dissolve. So again, reactants are favored and the solids are on the reactant side. So a KSP less than 1 means the solid doesn't want to dissolve, which means it's insoluble. Okay? And in our solubility rules, all we said was, ooh, it's insoluble. We can now say, oh, how insoluble are you? And it gives us a quantitative variation of everything that we've done in the past. All right, this next one, we have something called the reaction quotient and the ice table. Okay, the reaction quotient and the ice table. And I'm going to do those in another video. But you know what? I'm going to start with the ice table. All right, until next time, jolly out.